In this lecture, we use second-order Runge-Kutta methods to illustrate how to derive recursion formulas for approximating the solution to linear first-order initial value problems. Second-order Runge-Kutta methods generate approximate solutions that are made up of discrete points. Let the initial value problem be given by the differential equation y prime of t equals f of ty with y of a equal to y sub 0. To simplify the discussion, we use a uniform step size delta t so that we set delta t equal to a positive constant h. And so we use the partition points or nodes t sub k starting with t sub 0, which we set equal to a, t sub 0 is less than t sub 1, etc., etc., etc. Let y of t sub k be equal to y sub k, where k is a non-negative integer. The recursion for Euler's method or simple Euler's method can be written as y sub k plus 1 equals y sub k plus h times f of t sub k y sub k with an error that is of order h squared. The term h times f of t sub k y sub k represents the change in y from t equals t sub k to t equals t sub k plus 1 along the tangent line at t equals t sub k, and so h times f of t sub k y sub k is an approximation of the change in y along the graph of the exact solution. Second-order Runge-Kutta methods replace the term h times f of t sub k y sub k with a weighted average between two tangent slopes taken at 2 points that might be on the graph of the exact solution. In this lecture, we will show how to determine the weighted average between the two tangent slopes. Second-order Runge-Kutta methods assume that y sub k plus 1 equals y sub k plus alpha times h times f of t sub k y sub k. Then we have the term beta times h times f evaluated at t sub k plus r times h, y sub k plus s times h times f of t sub k y sub k. While f of t sub k y sub k is the tangent slope at the base point at t equals t sub k, roughly speaking, the factor f of t sub k plus r times h, y sub k plus s times h, times f of t sub k y sub k is like the tangent slope at some future value of t. The coefficients alpha, beta, r, and s are still to be determined real numbers. We first write y of t sub k plus 1 using a Taylor series around t equals t sub k, so that y of t sub k plus 1 equals y of t sub k plus y prime of t sub k times the quantity t sub k plus 1 minus t sub k plus y double prime of t sub k divided by 2 times the square of t sub k plus 1 minus t sub k, and then we have the error term, which is of the same order as the cube of the difference between t sub k plus 1 and t sub k. We replace y of t sub k plus 1 by y sub k plus 1. We replace y of t sub k by y sub k. T sub k plus 1 minus t sub k is equal to h. Y prime of t sub k equals f of t sub k y sub k, so that y double prime of t sub k is the derivative of f with respect to t evaluated at t sub k and y sub k. By the derivative of f with respect to t, we mean the total derivative of f with respect to t. We apply the chain rule to find this total derivative. The first term in this total derivative is the partial derivative of f with respect to t, followed by the product between the partial derivative of f with respect to y and the derivative of y with respect to t, or y prime of t. Y prime is f, so that the total derivative of f with respect to t is given by this equation. We denote the partial derivative of f with respect to t as f sub t, and the partial derivative of f with respect to y as f sub y. Therefore, a preliminary form of the recursion is given by y sub k plus 1 equals y sub k plus h times f of t sub k y sub k plus h squared divided by 2 times the total derivative of f with respect to t, which we replace with this expression, and multiply out. This second-order Taylor polynomial approximation will have an error of order h cubed. We continue to determine the recursion for y sub k plus 1 using this assumption for the second-order Runge-Kutta method. We expand this part using our good friend the Taylor series at t sub k, y sub k. This quantity is equal to f of t sub k, y sub k plus f sub t, or the partial derivative of f with respect to t, evaluated at t sub k, y sub k, times the change in t, which is r times h, plus f sub y, or the partial derivative of f with respect to y, evaluated at t sub k, y sub k, times the change in y, which is s times h times f of t sub k, y sub k. Since this is a first-order approximation, the error will be of order h squared. The first two terms in the recursion for y sub k plus 1 are y sub k and alpha times h times f of t sub k, y sub k. We replace this part with its Taylor series equivalent. We get this equation for y sub k plus 1. We multiply this out and rearrange the terms on the right side of the recursion to get this expression for y sub k plus 1. The error is of order h times h squared, or h cubed. We compare these two expressions for y sub k plus 1. The coefficient of f of t sub k, y sub k here is h. The coefficient of f of t sub k, y sub k here is alpha times h plus beta times h, and so alpha plus beta must be equal to 1. The coefficient of f sub t of t sub k, y sub k here is h squared divided by 2. The coefficient of f sub t of t sub k, y sub k here this time is beta times r times h squared, so that beta times r must be equal to 1/2. The coefficient of f sub y of t sub k, y sub k times f of t sub k, y sub k here is h squared divided by 2. The corresponding coefficient here this time is beta times s times h squared, so that beta times s must also be equal to 1/2. And so we have a system of equations in the unknowns alpha, beta, r, and s. This system of equations has infinitely many solutions. So let's check out some of the frequently used sets of values of alpha, beta, r, and s. If we choose alpha to be equal to 0 and beta equal to 1, with r and s both equal to 1/2, we get what is called the midpoint method. The recursion for the midpoint method has y sub k plus 1 equal to y sub k plus h times f evaluated at t sub k plus half as step size, or h over 2, and at y sub k plus halfway along the tangent line, or h over 2 times the tangent slope f of t sub k, y sub k. This pair of coordinates is supposed to be the coordinates of the point on the graph of the exact solution halfway between t equals t sub k and t equals t sub k plus 1. In reality, it is the halfway point along the tangent line. And so this quantity is an approximation of the tangent slope at the halfway point on the exact solution, so that what we have going on here is some sort of mean value theorem type thing. If we set alpha and beta to be both equal to 1/2, with r and s both equal to 1, we get the modified Euler, or the improved Euler method. It is also frequently called Heun's method. For this method, y sub k plus 1 equals y sub k plus h over 2 times the quantity f of t sub k, y sub k, plus f evaluated at t sub k plus h and at y sub k plus h times f of t sub k y sub k. This part of the modified Euler recursion represents the simple Euler approximation for y sub k plus 1. And because of this, the modified Euler method is also referred to as a predictor-corrector method, since one first makes a prediction, in this case, using the simple Euler method as to what y of t sub k plus 1 might be. We call this predicted value y sub predictor or simply y sub p. Then there is the attempt at correction by averaging out the supposed tangent slopes at t sub k, y sub k, and at y sub p. The error for both these methods is of order h cubed, since they are both based on a second-order Taylor series approximation.